In this video, we're going to learn how to use Newton's laws of motion to solve physics problems. Let's look at the problem-solving steps that we want to follow. And these are important. You want to follow these anytime you're solving a problem with Newton's laws. Step 1. Draw a free body diagram for each object involved. So if you've got 3 objects in the problem, you need to draw a free body diagram for each of the objects. As we know, free body diagrams show only the forces acting on the object, not forces that the object is exerting on a different object. The second step, choose an x and y axis that simplifies the calculation. Let me show you an example of where we need to do that. Let's say we have an object sliding down an incline. If we use our standard axes of y being the vertical axis and x being the horizontal axis, then as this object slides down the incline, it would be moving both in the x and the y direction. And that makes it much more difficult to analyze the problem. So instead, what we do in the case where we have objects on an incline is we rotate our axes. So we make the x-axis be along the incline and the y-axis perpendicular to the incline. And as you'll see when we start doing some of those types of problems, that dramatically simplifies the analysis. To find which direction is positive, let me talk about the type of problem where we have to do that. Let's say we have a pulley and we have 2 masses, M1 and M2, hanging on that pulley. Now, depending on what the relative masses are, that system may go in this direction or it could go in that direction. But the important thing is that you'll notice that when this object is going up, this object is going down. And so what we need to do is we need to define what direction is going to be the positive direction of motion for both objects. So if I call up the positive direction for object 1, then I need to call down the positive direction for object 2. Since they're moving together, we want them to have the same acceleration or the same velocity, and therefore we have to define it in that way. Once we've done those things, if necessary, then we need to resolve our forces into their x and y components. Remember that when we use Newton's second law, that the net force is equal to the mass times the acceleration, invariably what we're doing is we're writing that out separately for each component. And so in our case that will be x and y components. And then finally we apply Newton's second law separately for each component for each object. So if you've got 2 objects in the problem, you'll have to write down Newton's second law 4 times, the x and y direction for each object. Let's look at an example and apply our problem-solving steps. In this particular example, a 1.2 kilogram block is pulled with a force of 3 newtons as shown. What's the acceleration and what's the normal force on the box? And we're to assume that there's no friction. The first step then is always to draw the free body diagram. Remember that to draw a free body diagram, we simply use a dot to represent the object, and then we draw all of the forces acting on the object. In this case then we definitely have mg, the force of gravity, acting down. The block is on a surface, so we have the normal force, Fn, acting up. And then we also have an applied force that is at an angle with respect to the positive x-axis. That's our free body diagram. Now, anytime we have a force that's not only in the x or only in the y direction, we need to break that force into its components. You'll notice that in this case that's Fa. Let's go ahead then and write down the components of Fa. The x component of Fa would just be Fa cosine theta using our trigonometry knowledge, and the the y component of Fa would be Fa sine theta. Okay, so now we've drawn our free body diagram. We've looked at any forces that we need to break into components, and we've done that. Now we're going to write down Newton's second law for each component. So your next step should be write F net x equals max and F net y equals may. Let's go ahead and work on the x direction. When we're trying to figure out what goes in for F net x, we simply want to look at what are all the forces or components of forces that are acting in the x direction. Notice that the only force acting in the x direction is the component of Fa. Since it's to the right, we'll put in positive Fa cosine theta. So that is equal to max. One of the things we're trying to find is the acceleration. You'll notice I can now solve that for the acceleration. Ax is Fa cosine theta divided by m. Remember, we always want to solve algebraically, fully, before we plug in the numbers. At this point, then, I can go ahead and plug in the values. We've got 3 newtons for Fa, the cosine of 32 degrees. Again, we want to be in degree mode, divided by the mass of 1.2 kilograms. And we find that the acceleration is 2.1 meters per second squared. Now let's work on the y direction. We're being asked to find the normal force. Here we have to be a little bit careful. What forces are acting in the y direction? Well, definitely Fn is acting up. Mg is acting down, so minus mg. But don't forget about this component of Fa that's also in the y direction. That's positive, so I'm going to write plus Fa sine theta, and that equals may. Now, what is the acceleration in the y direction? Well, we can assume in this problem that the block is not going down through the table or lifting up into the air, and therefore we can go ahead and assume the acceleration in the y direction is 0. Therefore, now I can solve for the normal force. Fn is equal to mg minus Fa sine theta. I want you to think about that result for a minute before we plug in the numbers. Notice that if we hadn't had this pulling force, then we would have just had that Fn was equal to mg. But because part of what we're doing with that pulling force is pulling up, the ground doesn't have to exert as much force. And that's why the normal force is mg minus the amount that we're pulling up. We can now plug in the values. We've got a mass of 1.2, g is 9.8, and then minus 3 newtons times the sine of 32. And if you work that out, you should get 10 newtons. Notice the steps we went through. We drew the free body diagram. We then figured out which forces needed to be broken into their components and did that. Then we wrote down Newton's second law for each component, and then we filled them in. Let's look at another example. In this problem, we have an applied force being applied to 2 blocks that are in contact with each other. And once again, there's no friction. We're asked for 2 things. What force does the 20 kilogram block exert on the 10 kilogram block, and what is the acceleration? Let me remind you of our notation that we talked about when we talked about Newton's third law. So the force the 20 kilogram block exerts on the 10, I would call that F12, the force that block 1 exerts on block 2. Okay, we know what our first step is. Our first step is to draw the free body diagram for each object. So let's go ahead and do that. For object number 1, we have the normal force acting up. I've got to call that Fn1 because there are two different normal forces in this problem. That's really important to be careful with your subscripts. We also know that we can put the weight of the object, the force of gravity, or m1g. Again, make sure that you get that subscript. Acting to the right on block 1 is the applied force. And then there's one other force on block 1, and that is the fact that block 2 pushes back on block 1. Let's look at the free body diagram for block 2. For block 2, we've got m2g and Fn2. Now, we don't have Fa because Fa is not directly acting on block 1. However, on block 2. However, there is a force to the right on block 2. That's the force that block 1 exerts on block 2. And just to remind you of what we talked about with Newton's third law, this force and this force are an action-reaction pair. Therefore, we know the magnitude of F21 and F12 are the same. Now, in this particular problem, we don't really care about what's going on in the y direction because we're only asked about the acceleration and F12, and those are both in the x direction. Therefore, we only have to write down Newton's second law twice, once in the x direction for object 1, and once in the x direction for object 2. Notice my notation. F net x1, that stands for the net force in the x direction on object 1. And F net x2, the net force in the x direction on object 2. The next thing we're going to do is what we always do, is let's figure out what the net force is. If we look at object number 1, we see that Fa is to the right and F21 is to the left. So we'll write minus F21, and that equals m1a. We'll do the same thing for object number 2. For object number 2, there's only one force acting in the x direction, which is F12, and that equals m2a. So we've got two equations. Let me copy these equations over to the next slide. So we have Fa minus F21 is equal to m1a, and F12 is equal to m2a. Now, remember, we're trying to solve for F12 and a. We've got two equations, so we can solve for two unknowns. At first, you look at this and think we have three unknowns, F21, F12, and a. However, we know from Newton's third law that F12 and F21 are related. So here's the question. Is F21 equal to minus F12, or is F21 equal to F12? Go ahead and think about that for a minute, and then restart the video. My guess is that many of you selected this because Newton's third law says the forces are equal and opposite. However, the correct answer is this, and let's take a look at that. So again, Newton's third law says the forces are equal and opposite. So that's definitely correct. However, remember something that we said in a previous video. Our symbols represent magnitudes. So in other words, we've already put in the opposite part, right? Why was this negative? Because we said the direction was to the left. So we've already put that in. Therefore, The symbol itself is the magnitude, and the magnitude of the two forces, F21 and F12, are positive. So that's a really important thing to remember. This is not correct. When we're ready to substitute in so that we get down to two unknowns, we want to understand that F21 and F12 mean the same thing. They're the magnitude of that contact force. Once we've sorted that out, we can go ahead and solve the problem. So let me again write down our two equations. We had FA minus F21 equals M1A, and we had F12 is equal to M2A. What I'm going to do is I'm going to now take that first equation and rewrite it, but writing it as F12 instead of F21 since they're the same. So I have FA minus F12 is equal to M1A. And now what I'm going to do, so let me just make a note since F21 equals F12. Now what I'm going to do is to solve this, I'm going to add these two equations. Now, you guys have learned how to solve two equations, two unknowns before, but you probably haven't done it this way, or you might not have thought to do it this way. It actually works really well in Newton's third and second law problems to add the equations when you're trying to solve for one of the variables. The reason for that is that F12 is going to cancel out. And in fact, always those action-reaction pairs should cancel out when I'm adding up all of the equations. So it's kind of a nice check. So you'll notice when I add the left-hand side, I get FA plus F12 minus F12. So I just get FA on the left. And then on the right, I get M1A plus M2A. Again, I'm just adding these two equations up. Add the left-hand side, add the right-hand side. Now I can go ahead and solve for A algebraically. Factoring out an A and dividing, I get that the acceleration is FA divided by M1 plus M2. I want you to notice that that makes sense, because shouldn't the answer be the same as if I replace these two objects with one object with a mass of 30? And you'll notice that's what the algebra gets us to. I'll just let you know what you get if you plug in here. You get 0.17 meters per second squared. Now, once I have my answer for A, I can go back to either of my two equations to solve for F12. And obviously, I'm going to use the top one because it's easier. So F12, the force that object 1 exerts on object 2, is simply equal to 10 times 0.17, or 1.7 newtons. Let's look at the following conceptual question. What is the tension in the rope? So first of all, let me tell you what we mean by the tension in the rope. That's the way we phrase it in physics, but basically it means the force the rope exerts at each end. And so when we think about what a rope does in this case, it's simply transferring a force from one of the objects to the other. Let me talk about the notation that we use for tension. Some books use capital T for tension, but that's actually a bad notation, because later on in the course we'll need capital T to represent period. The period is the time it takes for an object to either oscillate back and forth once or go around in a circle once. So I'm not going to use that notation. I'm going to use F subscript T, and I'd like you to use that as well. Go ahead and pause the video and see what you think the answer is here. All right, let's go through this together. Often, the most common answer when I ask this in a class setting is B, but B is incorrect. The correct answer is A. And let's see how we can figure this out. To figure this problem out, I just need to look at one of the masses. So let's look at mass number 1. The net force on mass number 1 in the y direction is m1a. Now, in this particular problem, you'll notice the masses are identical. So we know that the object is not going to move, or neither object is going to move. In other words, we know the acceleration is equal to 0. Let's draw the free body diagram for mass number 1. There are only two forces acting on the object. There's the tension acting up, and there is the weight of the object acting down. Therefore, we have Ft minus m1g. But again, the acceleration is 0, so that equals 0. And therefore, the tension is equal to m1g, or 1 times 9.8. So 9.8 newtons is the correct answer. Think about the way that the rope is really just transferring that downward force that object 1 is exerting to the upward force on object 2 and vice versa. Okay, so it's not double, it's just 9.8. Again, if you analyze this for object 2, you'll get the same answer. So that's the tension. Let's look at a more complicated problem. Now we've got two masses hanging over a pulley. We say that the pulley and the rope are massless. That means basically we can just ignore their physical properties. And we now want to figure out what is the acceleration of the system and what is the tension in the rope. Well, we know that in this case the objects are going to accelerate. Remember, there's an extra step when we have two objects moving together in a situation like this. We've got to specify what we're going to refer to as the positive direction. So I'm going to define up as positive for m1. And therefore down is going to be positive for m2. And we'll see where that comes into the solution here in just a minute. Step 2. Let's draw the free body diagrams. They're pretty straightforward here. The free body diagram for object number 1 is that there is the tension and there is the weight of the object m1g. For object number 2, looks the same. We've got the tension. So notice we don't put a subscript on the tension like 1 or 2, because the tension is the same everywhere in the string. So whatever force the string is exerting on one side, it's also exerting on the other. So Ft is the same throughout. The downward force is the force of gravity on object 2, or m2g. So those are our free body diagrams. The next step, we know we need to write down Newton's second law for each object. And in this case, only in the y direction. Obviously, there's nothing going on in the x direction. So we've got the net force in the y direction on object 1 is equal to m1a, and the net force in the y direction on object 2 is equal to m2a. Okay, so now let's go ahead and identify what forces make up that net force. For object number 1, you'll notice that we have two forces acting. The tension is up and m1g is down. So Ft minus m1g is equal to m1a. For object number 2, here's where we need to be careful. We've defined down as positive. And therefore, when we write the sum, or the vector sum of the forces, the net force, we have to write that as m2g minus Ft. And that equals m2a. So notice we're saying that if m1 is accelerating upward, that's a positive acceleration. Well, in that case, m2 would be accelerating downward. That's also got to be a positive acceleration. So now we've determined our two equations. Notice here we've got two equations and we've got two unknowns, the tension and the acceleration. As I mentioned earlier in the video, the quickest way to solve these is to add the equations. I'm going to write Ft minus m1g equals m1a, and m2g minus ft equals m2a. You'll notice that when I add the left-hand side, the tensions go away. So I get m2g minus m1g, and that's equal to m1a plus m2a. Let me write that down again. We had m2g minus m1g is equal to m1a plus m2a. Well, now we can go ahead and solve for the acceleration. The acceleration is just going to be equal to, I'm going to factor out the m's and then divide. So I get a is equal to m2 minus m1. So I'm doing a couple algebra steps here, times g, divided by m1 plus m2. Before we go on and plug in the values, let's look at whether this solution makes sense. You'll notice that we defined this direction as positive. Therefore, notice that our acceleration is going to be positive as long as m2 is greater than m1. However, if m1 were greater than m2, then we would get a negative acceleration, and that would just tell us that they're going in this direction, right, which would be negative. Also, notice that if m1 equals m2, then a equals 0. And of course, we know that just from logic, that if the masses are the same, they don't move. All right. If we plug in the values, we get m2, which is 10 minus 5, times 9.8 divided by 10 plus 5, and we get an answer of 3.3 meters per second squared. Now, the second thing we were asked to do is find the tension. And in order to do this, we simply want to go back to either one of our equations and solve for t. I'm going to pick this one. Ft is equal to, or sorry, it was Ft minus m1g is equal to m1a, or Ft is equal to m1g plus m1a. And at this point, we then just need to plug in the values. So we've got 5 times 9.8 plus 5 times 3.3, and that equals 66 newtons to two significant figures. Let's look at the following problem. A car moving at 20 meters per second collides with a brick wall. The front of the car collapses on impact by a distance of 0.85 meters. The mass of the car is 1,300 kilograms. What was the magnitude of the force the brick wall exerted on the car? Well, when we first look at this problem, you might say there's not enough information to figure out the force because we weren't actually given any information about forces. Well, let's go ahead and see how to approach it. You'll notice that they've given us a lot of information about the speed and stopping distance of the car. And therefore, what we're going to have to do first is use kinematics to figure out what the acceleration of the car was during this time that it was hitting the brick wall. Once we know the acceleration, then we'll be able to determine the net force and ultimately the force that the brick wall exerts on the car. Let's get started. The first thing we're going to do is do the kinematics part. So I'm going to draw two different diagrams. Here is the car just as it gets to the brick wall. So it's just gotten there. The collision is just about to start. And now I'm going to draw the same thing, but now the car is mushed. So this is the last picture of the car after it's come to a stop. And now I'm going to go ahead and label these diagrams. So I'm going to keep track of where the back of the car is. And I'm going to say x naught then is 0. That's where I'm going to set my origin. Notice that after the collision, the back of the car has moved a distance. And that is the 0.85 meters because the front of the car has collapsed by that amount. Now, I know the initial velocity is 20 meters per second. And I know the final velocity is 0. Notice that I don't know t in this problem, and I don't know a, and that's what I need to find as my first step. If you go back and look at your one-dimensional kinematics equations, you'll see that the one you want to use is v squared is equal to v naught squared plus 2a x minus x naught, because that has both v and a in it and does not have t. We're going to do our usual thing here. Let's cross out what's 0. That's x naught is 0, and the final velocity is 0. And go ahead and solve algebraically for the acceleration. We get 2ax is equal to negative v naught squared, or a is equal to negative v naught squared over 2x. Notice, by the way, we're expecting the acceleration to be negative because the car is moving to the right and slowing down. Let's go ahead and figure out what that acceleration is. Well, it's negative 20 squared divided by 2 times 0.85. And when you calculate that, you should get an acceleration of negative 235 meters per second squared. Okay, we now know the acceleration. The next thing we want to do is now look at the force part of this problem. I'm going to use B for brick wall, and I'm going to use C for car. Let's draw the free body diagram for the car while it's crashing into the brick wall. We're going to assume this driver was on their cell phone. They weren't paying attention at all. They didn't see the brick wall, so they didn't even apply their brakes. The only force acting in the x direction is just the force that the brick wall exerts on the car. And obviously the force that the brick wall exerts on the car is to the left on the car. And of course the car is exerting a force on the brick wall to the right. The only other forces that we have here are the normal force and the weight of the car. So now we can go ahead and use Newton's second law. We know that the net force acting on the car in the x direction is equal to ma, and the only force acting is FBC. It's acting to the left, so I put in negative FBC. But then on the right-hand side, I know all the values. So I know enough to calculate the answer. In other words, FBC, to move that negative sign to the other side, is negative the mass, which is 1,300, times negative 235, which was our acceleration. And what we end up with is that the force that the brick wall exerts on the car is 3.1 times 10 to the 5th newtons. Notice, by the way, this is another illustration of the fact that what we mean by symbols, these force symbols like FBC, is they are magnitudes, because we found the magnitude of the force was 3.1 times 10 to the 5th. Obviously the direction was to the left, but we already put that in. That's why we don't get a negative answer. Let's look at one last problem. A 75 kilogram person stands on a scale in an elevator as it accelerates upward at 3 meters per second squared. What is her weight on the scale in newtons? So the first thing we have to understand is, how does the weight that the scale registers relate to what we know about? Well, what a scale registers is the force pushing down on it. But the force that the person exerts down on the scale from Newton's third law is the same in magnitude as the force the scale exerts up on the person. Well, that's just the normal force. So the normal force is going to give us the scale reading. Okay, and again, simply because of Newton's third law. So let's go ahead and draw the free body diagram for our person in the elevator. They only have two forces acting on them. The scale is pushing up on them, that's the normal force. The force of gravity is pulling down on them, mg. And so let's go ahead and write down Newton's second law in the y direction. The net force in the y direction is equal to ma. And we know the two forces, Fn minus mg, is equal to ma. Or then the normal force is equal to mg plus ma. And we'll go ahead and solve for the particular problem in a second, but I want to talk a little bit about that. Notice that your weight on the scale, if the elevator is not accelerating, it's just mg, as we would expect. But when the elevator is accelerating, the scale reading goes up. Now, I'm sure noticed this if you've been in an elevator in a tall building. When the elevator starts to accelerate upwards, you feel heavier. And if you brought a scale in with you and stood on the scale, you would see the scale needle would go up. On the other hand, you've probably noticed that when the elevator is up at the top and it starts coming down, it's accelerating in a negative direction, and you actually feel lighter at that moment. And that makes sense because this term would be negative. The scale reading will actually be less than normal. Let's go ahead and plug in the values. So we would get 75 times 9.8 plus 75 times 3. And that would give us a normal force of 960 newtons. And so if we had a scale that was measured in newtons instead of pounds, that would be the reading during the acceleration. I want to talk a little bit more about this problem. What would happen, what would the scale read if some evil person took a really big pair of scissors and cut the cable? So now the elevator is in free fall. Notice that if the acceleration is equal to negative g, when we calculate the force that the scale is exerting on you, the normal force, we'd get mg plus m times minus g. Or the normal force is equal to 0. In other words, you and the scale would simply be falling at the same rate, and so the scale would not be exerting any force on you, and you wouldn't be exerting any force on the scale. And in fact, you would be weightless. We call this apparent weightlessness because it's not like the force of gravity is not acting on you, but it will appear to you just like that your life in that elevator for the short amount of time that it has left is going to be just like an astronaut in a spaceship. You would literally be floating. If you took something out from your pocket and let it go in front of you, it would simply float in front of you because, of course, from the outside perspective, you and everything else in the elevator is simply in free fall. It turns out that that actually is the reason that astronauts are weightless in space. It's not because the force of gravity is no longer there. And so we're going to talk much more about that when we talk about gravity in Chapter 8. In our next video, we'll learn about some other things we need to know for forces, specifically how springs interact and also how to treat the force of friction.